All right, so when we're solving linear inequalities, so linear inequalities again are just like things that are not equal, right? But this is going to be really close to solving linear equations. So the same kind of concepts are going to be used. Solving linear inequalities is very similar to solving linear equations. We can think about attaching terms and factors to keep the scale imbalanced. So let me talk about that. So if we were solving a linear equation, um, like 3x minus 5 equals 7, we kind of thought about our properties of equality. We kind of thought about this as a big, like, teeter-totter, where we can attach the same terms and factors to both sides. And our goal, remember, our goal when we solve is to get x by itself on one side. So we want x equals. So we start decomposing the left side, the expression on the left. So we want to isolate the variable term. So we'll attach a positive 5 to both sides. And by doing that, the teeter-totter or the equation remains equal. So we get 3x equals 12. And then finally getting x by itself, we want to cancel that factor of 3. So we'll attach a factor of 3 in the denominator. And we'll get x equals, and then 3 or 12 divided by 3 is 4, right? Goes in there 4 times. So we get x equal to 4. Now, if we thought about this as an inequality, so what if we had 3x minus 5, say, is less than or equal to 7? So we would still solve this because equal to is still part of less than or equal to, correct? So what we do then is we kind of think of this teeter-totter, and I'll just put a little diagram down here. Think of a teeter-totter where the one side is heavier than the other. So it's kind of like this. The teeter-totter would kind of look like this, where the heavy side is on the ground and the light side is up in the air. And this would be a teeter-totter where we would have strictly less than. So if we think about it, we want to use properties of inequalities to basically keep not the equation equal, but the inequality true. So keep the imbalance of the teeter-totter the same, true or the same. So if a scale already starts out with the heavier on the right side, we have a less than, then I should be able to, again, think of the goal. My goal is to get x on one side again. And as long as I don't change the inequality, which you might be thinking, when would I change the inequality? But if we add 5 to both sides, then of course my teeter-totter remained the same. It would still be imbalanced. So isolate the variable term like I did before. The inequality still remains the same. And then dividing by 3 on both sides, and I get x is less than or equal to 4. So the concept is the same. Whether I keep the teeter-totter balanced, I can attach terms and factors to both sides to make sure the teeter-totter stays balanced. Or if it's an inequality, it keeps the imbalance the same. But there is, and again, it's linear, it's very similar. We have to think about that. It's very similar. So a lot of times we do the same thing, but all right. So I have the goals on the right side to solving a linear inequality. We'll simplify each expression. isolate the variable term on one side, and then isolate the variable factor. So again, the goals are the same as solving equations. When I get an answer with an equation, when I get an answer, I'm basically done. But when I get an answer to an inequality, we always want to equate that inequality and visualize it with a number line. So if it's less than or equal to 4, then it's going to be a solid circle at 4, and then everything to the left, right? So the solid circle, because it's equal to, and then less than would be left. But then we also want to use interval notation to get used to what that notation is, and get used to using it and seeing it. Remember interval notation, the starting point? Well, this arrow is going to the left, which signifies negative infinity. And the right endpoint, or the biggest value, is 4. And since it includes it, we use a bracket around that 4. So every time we solve an inequality, we always want to graph on a number line and then also write an interval notation. All right, so I want to talk about the compositional properties of equalities. And it's the same thing as the compositional properties of equations. So like I said, we can attach the same terms and factors to both sides, make sure we do it to both sides. But there is one case where the inequality is not the same. So I just want to go through an example, like a little side note here. If I could spell side note. So say we start off with like -3, we know is less than +5. So if we think about it, the teeter-totter in this one would look like that, right? Meaning the 5 would be heavy, so that side of the teeter-totter is down. The -3 would be light, so that side is up. And if we think of these as weights on a scale, then it makes sense that we can add and subtract. Like if we add 7 to both sides, the left side would be 4 and the right side would be 12, and 4 is still less than 12. The teeter-totter would never change. Even if we multiply or attach a factor, if we multiply, say, by -2 on both sides, then, by 2, sorry, we'll do -2 in a second. But if we multiply by 2 on both sides, this would become -6. The left side would be -6 and the right side would be 10. And still the teeter-totter would be this way, right? The 10 is heavier than the -6. But what happens when you multiply by a -2 on both sides? So if we multiply both sides by -2, on the left side becomes +6, and on the right side becomes -10. And what happens to our teeter-totter, becomes -10. And what happens to our teeter-totter is that now the left side is bigger than the right, and this is less than or greater than. So our inequality switches, because when you multiply by a negative number, it changes the sign, and it'll do that every time. So the only thing we need to worry about when we're working with inequalities is that when we attach the same negative factor, so it's multiply or divide by a negative number, then we reverse the inequality symbol, right? So that's the only thing we need to worry about with inequalities. So let's go through and solve this one, and we'll see what we're talking about. It says solve the following inequalities, graph the solution set, and write the solution in interval notation. So again, when we're going to solve, our goal is to get x on one side. All right, so again, we're going to isolate the variable term. So I'm going to get rid of this 8. We'll zero that out on both sides, and we're left with -3x is less than or equal to -6. And we don't change the sign because we're just attaching a term. But when we want to solve for x, we know we need to cancel that -3. We need to attach a negative factor, or a negative factor of -3 to the denominator, divide by -3. When we do that, then we need to take our inequality and switch it. This inequality is now going to change to greater than or equal to. So the -3's cancel. -6 divided by -3 is +2. So we get x is greater than or equal to +2. So if we check this, there's two things we actually have to check. So the first thing is to check if x equal to 2 solves the equality 8 minus 3x equals 2. And this is basically the boundary. Are we getting the correct boundary value or endpoint? So if we solve this, again, very quickly, we'll isolate the variable term. I get -3x equals -6, dividing by -3 or canceling the -3, we get x equals +2. So that checks, right? We could solve it again, or we could just plug the number in. If I plug the number in, I get 8 minus 3 times 2. Is that equal to 2? So we'd have 8 minus 6 equals 2, so we're good. So again, when we check a value, we just plug it into the equation and see if the left and right side are equal. But the other thing we need to check is we also need to check the inequality. So we need to check the inequality x is greater than 2. So if that solves 8 minus 3x is less than 2. So what we need to do is pick a number. Let's say we pick any number greater than 2, like x equaling 5. So when we plug that in, we get 8 minus 3 times 5, right? Is that less than 2? So we want to check this. We get 8 and a -15, which is -7, and that's definitely less than 2. So by switching the inequality sign, we do get a true solution or a true answer. So the last thing we're going to do is just graph on a number line. So again, on the number line, we only need to show the boundary point, the boundary. So it starts at 2, and it's a solid circle because it's equals, right? It has greater than or equal to. And if it's greater than, I want everything to the right. So this would be a graph of the solution. And then in interval notation, it starts at 2 and goes to infinity. So the 2 is with the bracket because it includes it. It starts at 2 and goes off to infinity. All right, so in the next lecture, we'll go through some more examples on solving this, but the only thing we need to worry about with inequalities is that if we ever multiply or divide by a negative number, or we attach a negative factor to both sides to solve, then we have to reverse the inequality symbol.